Here is a number that should stop you for a moment. According to measurements taken by DNS operators over the years, somewhere between 80 and 90% of all DNS queries that arrive at a recursive resolver are answered from cache, without ever contacting an authoritative name server at all. Think about what that means. The elaborate resolution machinery we walked through, the root servers, the TLD servers, the authoritative name servers, all of that infrastructure exists for the minority of queries that can't be answered from memory. The majority of the time, the system has already done the work, stored the result, and is operating from what it remembers. That's caching. And it is one of the most important engineering decisions in how DNS was designed, a decision that makes the system fast enough to be invisible to users, scalable enough to handle the entire internet, and complex enough to create a whole category of problems that we're going to spend 2 videos exploring. This video is about how caching works and why it was designed the way it was. The next one is about what goes wrong when the cache is wrong. Let's start from first principles, because caching is a general idea that applies far beyond DNS, and grounding it properly will pay off. A cache is a store of previously computed or previously retrieved results kept in a location where they can be accessed faster than recomputing or re-retrieving them from the original source. The word comes from the French cacher, to hide. A cache is, in a sense, a hidden store. It sits between you and the expensive operation you're trying to avoid repeating, intercepting requests and returning stored answers when it can. Caching shows up everywhere in computing, at every level of the stack. Your CPU has cache memory, tiny, extremely fast storage that holds recently used data, so the processor doesn't have to go all the way to main memory constantly. Your operating system caches file data in memory, so disk reads are fast. Your browser caches images, style sheets, and scripts, so it doesn't re-download them every time you visit a page. Content delivery networks cache entire web pages at servers close to users, so requests don't have to travel to the origin server. In every case, the motivation is the same. The original source of the data is either slow to reach, expensive to query, or both. Storing a copy closer to where you need it makes repeated access faster. The trade-off is always the same too. The cached copy might become outdated. The original source might change, and the cache might not know about it. This trade-off, speed versus freshness, is the fundamental tension at the heart of every caching system ever designed. Let's put the performance problem in concrete terms. Without caching, every single DNS query would require a full resolution walk, stub resolver to recursive resolver to root, root to TLD, TLD to authoritative server back up the chain to you. In the best case, each of those network round trips takes somewhere between 10 and 50 milliseconds, depending on geography and network conditions. A full cold resolution might cost 50 to 150 milliseconds in total. That sounds fast, and for one query, it is. But now consider that a modern web page might require dozens of DNS lookups. Not just the main domain, but every third-party resource the page loads. Analytics scripts, advertising networks, fonts, CDN assets, embedded widgets, social sharing buttons. Every single one of those might have a different domain name that needs resolving. If everyone required a full cold resolution, you'd be adding seconds to every page load just from DNS alone, and that's for a single user. Now scale to a recursive resolver serving millions of users. Imagine every one of those users triggering full resolution walks for every domain in every page they visit. The authoritative name servers for the most popular domains, Google, Facebook, Amazon, would be fielding billions of queries per day from recursive resolvers alone. The root name servers, being queried at the start of every cold resolution, would be handling an incomprehensibly large flood of traffic. The numbers simply don't work without caching. DNS at internet scale is only possible because the vast majority of queries are answered from memory, long before they ever reach an authoritative source. So how does DNS caching actually work? Let's trace through the mechanism precisely. When a recursive resolver performs a full resolution, works through root, TLD, authoritative name server, gets back an answer. It doesn't just forward that answer to the stub resolver and forget about it. It stores the answer in memory. keyed by the domain name and record type. The next time any stub resolver asks the same question, what's the IP address for www.example.com, the recursive resolver checks its cache first. If it has an entry for that exact name and record type, and if that entry hasn't expired, it returns the cached answer immediately. No root query, no TLD query, no authoritative server query, just a cache hit, returning an answer in microseconds rather than milliseconds. This is the core loop of DNS caching. Resolve once, cache the result, serve from cache for subsequent requests, only go back to the source when the cached answer expires. But there's a crucial question embedded in that last sentence. When does the cached answer expire? How does the resolver know when the information it has is still valid? The authoritative name server isn't going to proactively notify every recursive resolver in the world whenever a record changes. There's no push mechanism. The resolver is on its own. The answer is a number attached to every DNS record, called the TTL. TTL stands for time to live. It is, in the simplest terms, the number of seconds that a cached record should be considered valid. Every DNS record has a TTL attached to it, set by the authoritative name server when the record is defined. When a recursive resolver receives a record, it also receives the TTL. The resolver stores the record and starts a countdown. When the TTL reaches 0, the cached record expires, and the next query for that name will trigger a fresh resolution from the authoritative server. So if www.example.com has an A record with a TTL of 3600, that's 1 hour, a recursive resolver that just resolved it will consider its cached answer valid for the next hour. Any query for www.example.com that arrives within that hour gets the cached answer. After the hour is up, the next query triggers a fresh lookup. Critically, the TTL counts down in real time. If the authoritative server sets a TTL of 3600 and the recursive resolver caches the record, it stores it with a full 3600-second lifetime. If another recursive resolver, somewhere else in the world, fetched the same record 30 minutes ago, its cached copy has only 1800 seconds left. The TTL is not reset when a resolver serves a cached answer to a client. It continues counting down from the moment the resolver first received the record. This is important when your stub resolver asks your recursive resolver for a record. The TTL you receive, if the resolver passes it through, reflects how much time is left on the record, not a fresh 3600 seconds. You're seeing the residual lifetime of a record that's been aging in someone's cache. And this means that at any given moment, resolvers all around the world may have the same record in cache with different amounts of time left. Some just fetched it. Some fetched it an hour ago and it's about to expire. This is normal, expected, and it's the beginning of understanding why DNS changes don't propagate instantaneously. Now let's look at where caches actually live, because there isn't just one cache in the path between you and an authoritative name server. There are several, layered at different points in the resolution chain. The first cache is on your device itself, in the operating system's stub resolver. Your OS maintains a small local DNS cache. When your browser asks for maps.google.com and the OS already resolved it recently, it doesn't even go to the network. It returns the cached answer from local memory. On most operating systems, you can inspect this cache. This local cache is the fastest of all. No network involved at all, just a memory lookup. The second cache is in the browser itself. Modern browsers maintain their own independent DNS cache, separate from the OS cache. Chrome, Firefox, and others each keep a list of recently resolved names with their own TTL countdown. This means that even if the OS cache has expired an entry, the browser might still have it. And conversely, if the browser cache expires a record, it might find a fresh copy in the OS cache without going to the network. Two separate caches, at the same level of the stack, potentially with different data. The third cache, the big one, is in the recursive resolver. This is the server your OS is configured to consult for DNS queries. Your ISP's resolver, or a public resolver like 8.8.8, handles queries from potentially millions of users, and its cache is correspondingly large and rich. Because many users are querying the same popular domains, The recursive resolver's cache for high-traffic names is almost always warm. There's almost always a recent, valid cached entry. The fourth cache is a more subtle one. Some authoritative name servers themselves cache the responses from other levels of the hierarchy. When your recursive resolver asks the TLD name server for the authoritative servers, that answer has its own TTL and gets cached. The recursive resolver doesn't need to ask the TLD every time. It only asks when that delegation record expires. So a complete chain from your browser to an authoritative name server passes through multiple caching layers: browser cache, OS cache, recursive resolver cache, and cached delegation records within the recursive resolver itself. In the vast majority of cases, the query never makes it past the first layer, where a valid cached answer exists. Now let's think carefully about what actually gets cached, because not all DNS information is cached the same way. First, A records and quadruple A records, the final address mappings, get cached at every level. These are what you're usually most interested in, and they're what we've been talking about. The TTL on these records controls how long resolvers hold on to the address before going back to check. CNAME records get cached as well, along with the final A record they point to. When a resolver follows a CNAME chain, it typically caches each step, the CNAME record pointing to the canonical name and the canonical name's A record, each with its own respective TTL. This means that a CNAME might remain in cache after the A record it references has expired, and the resolver will follow the cached CNAME to do a fresh lookup of just the canonical name. NS records, name server records, which tell resolvers which authoritative servers are responsible for a domain, are cached with their own TTLs. These tend to have longer TTLs because delegation changes are rare. An NS record might have a TTL of 48 or 72 hours. This means that even if a domain changes its authoritative name servers, resolvers around the world might spend days still asking the old servers. MX records, mail exchange records, are cached too, at whatever TTL the operator has set. If you change your email provider and update your MX records, there's a window during which some mail servers around the world will still try to deliver to your old mail infrastructure because they cached the old MX records. Every record type participates in the caching system. Every change to any DNS record propagates through the internet at the speed of TTL expiration, not instantaneously, but over a window of time determined by how long the old record was set to be considered valid. The TTL is therefore not just a technical parameter. It's a design decision with real operational consequences, and choosing it wisely requires thinking through the trade-offs explicitly. A short TTL, say 60 seconds or 300 seconds, means that cached records expire quickly. Changes propagate fast. Within minutes of updating a record at the authoritative server, most resolvers will have expired their cached copies and will fetch fresh data on the next query. The cost is performance and load. Every resolver has to go back to the authoritative server more frequently, generating more query traffic, more network round trips, slower response for queries that miss the cache. A long TTL, say 86-400 seconds, which is 1 day, or even 6-4800 seconds, which is 1 week, means cached records persist for a long time. The authoritative server sees far less query traffic, cache hit rates are high, performance is excellent. The cost is agility. When you need to change a record, the change propagates slowly. For a full day or a full week, resolvers across the internet are still serving the old answer to their clients. Neither extreme is right in all situations. The appropriate TTL depends on how often you expect the record to change, how critical fast propagation is, and how much load your authoritative server can handle. High-traffic records that rarely change, like the A records for major websites, often have moderate TTLs in the range of 300 to 3600 seconds. Records for infrastructure that almost never changes, like NS delegation records, often have TTLs of 24 to 48 hours. Records for services that need to be able to fail over quickly, load balancers, CDN endpoints, are often set with TTLs as short as 30 to 60 seconds. For services where uptime is critical, that's a worthwhile trade-off. There is also a practice, often called TTL pre-lowering, that smart operators use before planned changes. If you know you're going to change a DNS record in 2 weeks, you lower the TTL on that record well in advance. By the time you make the actual change, all the old cached copies with the old high TTL have long since expired. Then, after the migration is complete and stable, you raise the TTL back to a more efficient value. This technique, prepare by lowering TTL, change, recover by raising TTL, is standard practice for any DNS change that needs to propagate cleanly. The engineers who know to do this smoothly execute migrations that look effortless. We've talked about caching records that do exist, but there's another important category, caching the fact that something doesn't exist. If you query for a domain that has no DNS records, the authoritative name server doesn't just silently decline to answer. It returns a specific response indicating that the queried name doesn't exist. This response is called an NX domain response, non-existent domain, and this NX domain response can also be cached. The concept is called negative caching, and it's been a formal part of the DNS specification since the late 1990s. Without negative caching, every query for a non-existent domain would require a full resolution walk every single time. Given how many such queries happen, this would generate a significant flood of pointless traffic reaching authoritative servers. So far we've talked about caching as a performance feature with an inherent freshness trade-off, but there's another dimension to caching that's worth understanding, the security dimension. Because caches hold the answer to what address does this name map to, and because many systems trust those cached answers to make security-sensitive decisions, caches are also potential attack targets. The attack is called DNS cache poisoning, and it's one of the most important security vulnerabilities in the history of Internet infrastructure. The idea is conceptually simple. If an attacker can get a false record into a resolver's cache, then every user of that resolver gets directed to the attacker instead. The user tries to visit one legitimate address. The resolver returns the poisoned address. The user connects to the attacker's server, thinking it's the real thing. It's a form of man-in-the-middle attack at the naming layer. For years, this was achievable by exploiting predictable patterns in DNS query IDs. The identifiers attached to queries and responses to match them up. If an attacker could guess the query ID and respond before the real authoritative server did, they could inject a false record into the cache. In 2008, security researcher Dan Kaminsky discovered a variant of this attack that was far more efficient and dangerous than previously understood, and his disclosure triggered an emergency coordinated response across the DNS industry, one of the largest synchronized security patches in Internet history. The mitigations involved making DNS transactions more unpredictable, randomizing source ports and query IDs so that attackers couldn't reliably guess the right combination to inject a false response. But the deeper, more robust solution is a system called DNSSEC, DNS Security Extensions, which uses cryptographic signatures to allow resolvers to verify that the records they receive are genuinely from the authoritative source and haven't been tampered with. DNSSEC adoption has been gradual and incomplete. It requires setup by domain operators, and not all resolvers validate signatures even when they're present. But it represents the principled solution to the problem of trusting cached data from an unauthenticated source. The important takeaway here is that the cache isn't just a performance optimization sitting on the side of the resolution process. It's a central component of how DNS works, and its trustworthiness has direct security implications. Caching isn't neutral infrastructure. It's infrastructure that can be exploited if it's not designed and operated with security in mind. One more mechanism worth understanding: cache flushing. The ability to force a cache to discard its stored entries and fetch fresh data. Sometimes you've made a DNS change and you need it to take effect right now on your specific device without waiting for the TTL to expire. On most operating systems, you can flush the local DNS cache, clear all stored entries, forcing the next query to go back to the network. Most network teams know this command by heart because flushing the local cache is one of the first steps in any DNS troubleshooting workflow. But flushing your local cache only affects your device. Your recursive resolver, the one your ISP or public DNS service runs, maintains its own independent cache, and you cannot flush that remotely. If the recursive resolver has cached a stale record with a 3600-second TTL that still has 55 minutes left, there is nothing you can do from your side to make it expire early. Some DNS providers, particularly those targeting developers and enterprises, provide cache purge APIs that let domain operators manually invalidate specific records in the provider's resolvers. But this only affects that specific provider's resolvers. The global internet is full of hundreds of thousands of recursive resolvers run by ISPs, enterprises and public services, and most of them have no mechanism for external cache invalidation. The TTL is the contract. Once a resolver has cached a record with a given TTL, it is entitled to serve that record for the full TTL duration. You set the TTL when you publish the record. The resolver is honoring your stated intention. If you set a TTL of 86,400 and then need to change the record urgently, you're paying the price for having told the world, "Trust this answer for 24 hours. This is why TTL pre-lowering matters so much, and why the engineers who do it carefully before planned changes find DNS migrations smooth, while those who don't find them unexpectedly painful. Let's bring this together. Caching in DNS is not an optimization bolted onto an otherwise complete system. It is fundamental to how DNS functions at internet scale. Without it, the query volume would overwhelm authoritative servers, resolution latency would be perceptible on every page load, the root servers, 13 logical addresses handling the entire internet, would not be remotely feasible. But caching creates a consequence that cannot be fully engineered away. The system's view of the truth is always, to some degree, delayed. Every cache is a snapshot of reality at the moment the record was fetched. The authoritative records at the source can change. The cache doesn't know that immediately. It knows it eventually, when the TTL expires and a fresh lookup is triggered. But in the window between a change at the authoritative source and the expiration of cached copies, different parts of the internet are operating on different beliefs about what a name means. That window, the propagation delay, the period of inconsistency, is not a bug. It's a direct, deliberate consequence of the design decision to cache. You can make the window shorter by setting low TTLs. You can pre-shrink the window with TTL pre-lowering. You can verify your own local state by flushing your cache. But you cannot make the window 0 while also having a cache. The two are incompatible. That's the fundamental tension, and it doesn't resolve, it only gets managed. That's caching. See you in next one.